think we're recording. So I want to start with some homework questions before we break back into groups and then go over those 4 questions from the next homework. So there was a question. I had a couple questions, a couple emails about the compressive strain. I think it's number 1 on the homework. So that whole purpose of that question is to show that the thing kind of breaks down when you have large compressive strains. You can't just randomly apply the definition. So there's a couple things you can do. So first would be you can actually compute. You have the change of positions of the corners, right? So you can compute what the deformation gradient is and compute the strain from that. Right? You know your displacements. Or you can also just you can take the negative of your answer, right? And that will give you a strain as well. Right? So think about it, play with it. Right? But there's no real magic there. The idea is just to show that when you have large compressive strains, the undergraduate notion of a simple tension test, strain defined from that, breaks down. Right? So other questions about that?
2.10.
2.10. Okay. Okay, so it says from the values obtained in exercise 2.9. So in 2.9 you calculated the Young's modulus along the different directions. Hopefully that was no problem. Right? Obtain a rough estimate of the Young's modulus of a polycrystalline aggregate, assuming there are only 3 orientations, and that they occur proportionally to their multiplicity factor. Okay, so is that the part that throws you off? So the multiplicity. Multiplicity. Why am I having trouble saying that? Factors. Is that the? Okay, so how many? This is just the number of symmetrically equivalents in FCC, right? So, right. How many 100?
Just 3.
Right? Yeah, you've got 3, right?
And then the negatives, yeah.
Right? Right? There's 3 100 type planes. Right? What about 110 and 111?
4 and 6.
Right? So if you draw out all your face diagonal planes and all your body diagonal planes, right? You have different numbers of those, right? So,
6.
right? So then, those are you're going to use those for the weighting factors for your average, right? And then the Voigt average and Royce average are just the, right, I have those three orientations. I'm just going to take the mean of those and the geometric mean, the arithmetic mean and the geometric mean. Right? Any other questions on the homework? Hopefully it should be very straightforward. And the okay, so let's, if there's no other questions on the homework, I'm going to pause the recording. We'll break back into groups momentarily and decide who's going to present each of the four to the class. So. Okay, so welcome back. I'm going to give an overview of question 1. It says the group came up with this solution, and the solution they came up with is a little complicated, and I can't verify that it's actually right without digging into it a little deeper. They've got the right idea, but I don't want to mislead anybody. So what we say is we've got copper, and I say plot for directions between 110 and 001. So let's draw our cube. So 001 is 0 in x, 0 in y, so it's lying parallel to the x3 axis, and 110 here. So this is 45 degrees, right? And I say plot the variation in Young's modulus for all the vectors in this plane, right? And so what we want to do is to find all the vectors. We want to, basically we can sample points along the corner of this, the edge of, where did it go? This is the only problem with doing this in PowerPoint is you have to do it in presentation mode, so you can't go back. Otherwise it stops the recording. So we want to sample points along this line. So these are points that have are 1, 1, say 1, 1, z, where z goes from 0 to 1, right? And those are your crystallographic directions of all the vectors that go like that. Right, so now you need to normalize these. Right? So 1 squared plus 1 squared plus z squared. Right? That gives me z plus 2. So I need to divide this by the square root of z squared plus 2. Right? So these are the vectors in that, on this part of the plane that we want to look at. Now, up here, right, this is z equals 1 now, right? And we have x equals y, right? And this goes from x equals y equals
0.
0.
X equals y equals 1.
Right. Yeah, so this goes from 0 less than equal to x equals y less than equal to 1. Right? So here we have x, 1. Right? This is x squared plus 1. Right? So the square root of 2x squared plus 1. Right? So now you want to plug this into your formula for the Young's modulus. Right? So E directional is 1 over S1111. Right? And you can just plug that into your formula and calculate it and then plot it. Right? So it's a little less convoluted than I think your approach is good, but I think you forgot the normalization. Right? So if you go back and normalize your direction vectors that you get, I think you should have the right answer. So you'll end up with something that looks almost like the trend, right? And in your notes, I show what it should look like, right? I give you the full 3D surface for the directional Young's modulus in the notes. Right, well, not exactly. I give you the 3D for C11, I think.
That's in the text.
In the text, yeah. So, compare it against that, right? It should make sense. Who's going to be doing group 2? Question 2. Someone brave.
Using that one.
Yeah. Yeah, come on up. Okay, so introduce yourself because people don't know.
Okay.
People can't see you.
Okay.
And then, so this bottom button here,
Uh-huh.
you gotta be careful. That is erase, and that messes things up.
Okay. Okay, I'll try. Yeah. Hopefully it's nothing wrong. Yeah. Okay, so yeah. So
Introduce yourself.
okay.
Excellent.
I'm Chao from the Dr. Guan School, and I'm the first year PhD student here. And the problem I have got here is to calculate the string of the string. We must to roll it to match the specific elastic modulus in the arrow, and we from the book we know that the SIG equal to the identity, and we have got the we got the elastic moduli, the C11 equals to 237 gigapar, and C12 and C44. So by using this equation, we can get the compliance moduli, the SIG. Like oh no, how do I erase
The bottom. This bottom. Hold that bottom button.
Yeah. Okay. Oh, I see. So we can get the like the S11 equals to C11 plus C12 divided by C11 multiply C11 plus C12 minus 2 C12 square, and S12 equals to negative C12 C11 C11 plus C12 minus 2 C12 square, and S44 is very simple, it's just 1 over C44, and we have already know the value of this C11, C12, and C44, so we can calculate the S11, S12, and S44. So
Did you actually invert the matrix by hand, or did you just look up the relationship?
yeah, by hand.
Okay. It's a 3 by 3, so it's not bad.
Yeah.
But still, you could just do it numerically as
Okay.
well.
Okay. Yeah, and then we can use the equation here, the ig S11 minus 2 S11 S12 minus 1 half S44 multiply Li 1 square J2 square J2 square. So the L1, J2, and LK3 here is the direction cosine. So in the 111 plane, they all equal to 1 divided by the square root 3, and so we can directly plug in this value.
That's right. Just
Okay. Okay. Yeah. So we can just plug the all of the value into the equation, so we can get the elastic moduli on plane 111 is it's around 284 gigaparsec.
okay. So be careful, right? You said plane 111. It's not the plane; it's the direction.
Oh yeah,
111, right?
direction.
So we have to be careful because the plane
Oh yeah.
right
Yeah.
implies a direction that's orthogonal to 111.
Yeah, it's the direction. Yeah, direction 111 has its elastic moduli, and then it says in the question it says the
So you start
it's
with
linearly it's the so so in the question it said if we roll this the iron sheet and the string has a linearly relationship with the elastic moduli. I think so. Yeah. So we can just simply plug the figure like this one. This is elastic moduli, and this is the string. And in the question it says if we roll like at the 200% string like this one, we can get the elastic moduli like the 284, and the initial elastic moduli is 209. So if we want
Can you real fast just sketch another axis with the same right? You can draw it on this either a second y-axis or a second plot.
Second plot.
Right, just show the volume fraction of 111. Right, the amount of 111. Yeah, so you're rolling. So it's so this is 111 percent, right? This is 0 and 100%. So at a strain of 200%, we know we're at 100%. And then at 0 strain, we're at some 111 that's close to 0. It's not exactly, because in a perfectly random texture, you still will have some 111, right?
Okay.
So the amount of 111 increases linearly with strain, and the amount of, so the modulus also increases linearly, according to the approximations that I set forth in the problem.
Oh, I see. Yeah. I didn't think too much because it's just tell us that it has a linear relationship. So I think maybe I can just plug this figure, and in the question they asked us to get the 260 gigapulse the elastic modulus. So there's 260. So we can get the string here. It's around like the 136%.
Okay, thank you. So question 3. Who's going to do it? Okay, Stan, say hello.
Hello. I'm Stan Bobit. I'm not really in any research group, so I'll be doing problem 3. So in the problem, there's a couple of assumptions made. Basically, you just said that those rods are close enough together that there's no moment that's going to develop as a result of that.
Okay, so the bottom, this one, it's kind of a real pain. The new pens are much better. So the bottom button erases, and the top button messes everything up.
All right. So anyways, we need to find the load in the structure. So there's a uniform load pulling down, so each bar is going to have a proportional amount of load that it's carrying. So with the current setup that we have, we know that the change in the length of A is equal to the change in the length of B. Since the bars are the same dimensionally, strain in A is equal to the strain in B. And if we just plug in our values for the strain in A and B, we have stress in A for the elastic modulus of A is equal to the stress in B over the elastic modulus in B. We know these values, so we can figure out the relationship in the stress values between A and B. So sigma A is equal to sigma B times EA over EB. So the stress in rod A is equal to 3 times the stress in rod B. And if we look at the yield strength for the steel versus the aluminum, it's actually less than 3 times the yield strength of B. So actually rod A will fail first, even though it's a stronger rod. And actually, if you go through and look at the maximum strain that each bar can handle, the strain in A is less than the strain in B. So next, we need to actually calculate the load out from that. So if we take that rod A is going to be the one to fail first, the maximum stress that we can have is 855 MPa, which is Pmax over A. So the max load that we can carry in A is 110 kilonewtons, and we know that since the stress in B is 1/3 of A, with the same cross-sectional area, P and B is 1/3 of P and A, and the P total is A and B, which would be 147 kilonewtons.
I don't recall offhand if that's the exact numeric answer, but it's the right strategy. So
There's a couple rounding.
okay, last group.
I can probably wing it. Oh, here they are. Good. All right, I am Elon Weiss. I'm in Dr. Wendell's research group. And problem 4 asks us to speculate about the relationship between elastic modulus and thermal expansion. And the way we decided to do that is to go to my good friend, the pair potential. Something like this. Bad, but it stimulates the point. This is the equilibrium radius, RE, and at 0K, our atoms sit at that radius all nice and snug-like. But if you were to raise up the temperature, they move. And they move according to some anisotropy between the compressive and the two sides of this curve. So they're not going to move straight up. Let's see if I can draw that line. There we go. They're actually going to move more like this. And this becomes some RU. This is an RE. And this becomes delta R. Now, if that curve changes, and if the curve is really deep, and lots of the R's match up, then for the same change in temperature, the change in RE is going to be less. And that is related to our thermal expansion. Young's modulus is defined as the second derivative of our energy with respect to radius, dr squared, evaluated at our equilibrium radius, divided by or not. And the first derivative of that, which is actually force, looks something like this. This is RE, and this ends up being the slope of that curve. And as the pair potential gets deeper and sharper, this slope increases, which in turn should make E go up. Now, because it gets deeper and sloper, the delta R that you can get, because this has a very small delta R that could possibly occur, this has a much larger one, our alpha L has to increase, or decrease, pardon me, as the depth of the well, DE increases.
Just thinking about the physical phenomena that occurs and how they're all these mechanical behaviors, right? Anytime you're dealing with bonding and elasticity, everything is intertwined and interconnected. So, right, it's an important thing to consider when thinking about alloy design, or functional. Right? You can't tweak properties independently most of the time. Right? You have to think about, and for mechanical properties, those, except for elasticity, right, which is intrinsic, and plasticity in single crystals, everything becomes tied with structure as well. Right? So when we're thinking about properties, it's the inherent bonding, right, the chemistry and the bonding, as well as the structure. Right? So it's the genetics and the epigenetics, or nature and nurture have to work together. And you can't tweak properties in isolation most of the time. And it's always going to change something else. So that's all we got for today. We're finishing up a couple minutes early for once. Unless there's any additional questions. Right? Hopefully these four are now very straightforward. I didn't only spend a couple minutes on them. Right? We're gonna work some. So just out of everyone's fun, does this? So my thoughts for Wednesday, is I was going to work a couple problems on viscoelasticity that kind of tie some of the ideas in the lectures together in a little more firm manner, and then do a couple of these group problems again. Does it seem valuable to you? Right? Working some of the homework problems in classes groups. Does that seem like a valuable exercise or a waste of your time?
I mean, I think it was valuable this time because now those problems are going to be straightforward.
That's the idea, right? I want questions. I want to do activities that relieve some of the homework burden and enhance understanding, right? So keep the feedback up to me, right? If you find that we're doing things in class that are not doing those two things, right? Then speak up and let me know, because then we can change. Right? The idea is I want the class time to be useful, right? Not just I can watch all the lectures online. There's no point in me coming to class. Right? So, okay, have a good couple days. We'll see you Wednesday.
I mean, then, so tomorrow, you said tomorrow after you was when you wanted to get together, right? Yeah. I think